In Chapter 9 of Restructured Electricity Markets, we will discuss in detail locational marginal pricing. We'll first formulate the optimal power flow problem, describe a simplification of it that is used in most markets, DC optimal power flow, describe the offer-based version of it, the offer-based optimal power flow or offer-based security constraint economic dispatch, give some examples, some properties of locational marginal prices, and then go on to discuss some topics such as congestion rent and congestion cost, contingency constraints, reactive power, losses, and then finally decomposition and linearization. As always, there are a few homework exercises at the end of the slides. So first, optimal power flow. This is a generalization of economic dispatch, and it's sometimes called security constraint economic dispatch, particularly in the context of the offer-based version. In this optimization problem, we consider a number of constraints on operation. So besides the generator constraints, there are limitations on the flows on transmission lines. There are capacities, each line has a capacity, and so limitations on the allowable flow on those lines between generation and demand can limit the feasible choices of generation. These constraints are typically due to maximum temperature limits on transmission lines. The temperature rise above ambient is due to thermal heating of the transmission elements, and that thermal heating is due to electrical losses. We'll typically think of these limits as being fixed and given. However, the rating depends on how long the flow of power is to be sustained and, of course, on ambient temperatures. If it's colder, one can inject more power along lines, cope with more heating because that heat is being dissipated more quickly. There are other issues besides thermal constraints, voltage constraints and constraints due to the need to maintain stability of the dynamics of the electromechanical generation transmission system. Those issues can also constrain operation. And although we could in principle represent them directly into our formulation, we will tacitly assume that they've been translated into what are called thermal proxy constraints. In other words, a constraint that looks like, has a similar form to a thermal limit, but is really a proxy for one of these other issues. So we'll have limitations on the flows, but in order to check whether or not the line flow and voltage constraints are satisfied, we need to actually be able to calculate what the power flow is and calculate what the voltages are if we have voltage constraints. In other words, we need to expand the detail of representation of the network by explicitly incorporating Kirchhoff's laws. We did this back in Chapter 3 in the formulation of the power flow equations in section 3.2.7. Flow of power on transmission lines incurs losses, and indeed it is the losses that produce the thermal limits. But a related but separate issue is that those losses mean that the power injected at the generators, not all of it gets to the load. And in particular, power flowing from remote generators to load may incur greater losses than the generation from a generator that is nearby to the load. This effectively changes the relative cost of generation depending on location, and it is a conceptually separate issue from transmission constraints. We'll consider that towards the end of this chapter. Besides real power generations, we could also consider adjusting any controllable elements in the system. Reactive power generations, for example, switch capacitors, anything that we could utilize to minimize costs and meet constraints. But we will fade a good deal of that detail into the background of our basic formulation. So, our formulation starts with variables, and in the decision vector we're going to represent real and reactive power generations at the generators. They're represented in the vectors P and Q. If we have a bus without generators, that could be represented by a generator with capacity 0, for example. We might either have specified demands of real and reactive power, or in the case of demand bids, we would have real and reactive power demand at the loads represented by the vectors D and E. Remember, in economic dispatch, D was the total demand summed across all of the loads, but now we need to specify the demand locationally at each bus, so D is a vector. Notionally, E, the vector of reactive powers, is also specified at each bus. Then we may have decision vectors for any other controllable elements, for example, the settings of phase shifting transformers and capacitors. We need to represent the voltage magnitudes at every bus in the system, represented in the vector U, and we need to represent the voltage angles at every bus in the system, except for the reference bus. Remember, the voltage angle at the reference bus is a constant, so if rho is the reference bus, the vector of unknown voltage angles is theta minus rho. Remember my notation, where I write minus a bus number, that means the vector including everything but that. When I write theta minus rho, for example, I mean the vector of all angles except at the vector rho, since that is known. We collect all of those variables into the decision vector x. X consists of P, Q, theta minus rho, and U. In the case of demand bids, it would be expanded to be D, E, the vector of real and reactive demands, P and Q, the real and reactive generations, and then theta minus rho and U. Remember from section 8.12.3.1 that we considered the voltage angles and magnitudes to be collected in a vector which notionally we numbered as subvector x np plus 1. In other words, the subvector after the last generation vector, and that would consist of theta minus rho and mu. As previously, let's let F be the total cost of generation. Although in general it's a function from Rn into R, the whole decision vector, typically F depends only on the entries of X corresponding to the real power generation, perhaps also on the bid demand, on the real power demand level. In some formulations, F might also depend somewhat on the reactive power generations and the reactive demands. F is separable, since the decisions at one generator do not usually affect the costs at other generators. So in that case, we could write Fx is equal to the sum from k equal 1 to np, in other words, across the generators, of Fk Pk, the sum of the costs of generating at Pk. In the case of bid demand, this becomes f of x is equal to minus the benefit of d plus the sum of the costs. And remember, since d is a vector, this should in turn really be thought of as the sum of the benefits summed across the benefits of the decisions at each bus. Since we're now including the voltage magnitude at the reference bus as a decision variable, we need to slightly redefine the power flow equality constraints compared to section 3.2.7. Our equations are really now, for all buses L, we have a function PL, which is a function of theta minus rho and U, and that function, which tells us the flows out along the lines from bus L, should be balanced by the real power generation at bus L less the real power demand at bus L. Similarly, there's a reactive power function representing the reactive power flowing out along all the lines connected to bus L. That should balance against the reactive power production at bus L and the demand at bus L. And again, PL and QL are defined similarly to equations 3.6 to 3.7. They simply sum across the buses connected to bus L. Again, U rho, the voltage at the reference bus, is now a decision variable, at least in principle, slightly generalizing the case in section 3.2.6.2 and the subsequent development in that chapter. J of L is the set of buses joined to a line by bus L. And we can collect those equations together into a vector equation similar to the form of 3.8, g of x equal to 0, where a typical entry of g is of either of the form PL of theta minus rho u minus PL plus DL, or of the form QL of theta minus rho u minus QL plus EL, and both of those are being set equal to 0 by the equality constraint. The decision vector X includes the real and reactive generations and possibly the real and reactive demands, as well as the voltage magnitudes and angles. We also will have inequality constraints. The simplest of these are limits on the entries in X. We might have a vector X underline, another vector X overline that represents the lower and upper limits on entries of X. For example, a voltage magnitude limit at bus L might be in per unit. The lower limit is 0.95 per unit, the upper limit is 1.05 per unit. And UL, the voltage at bus L, UL, is between 0.95 and 1.05. Similarly, a real power generation limit at a bus for generator L might be that PL is greater than or equal to 0.15, again per unit, and less than 0.7 per unit. We might also have functional constraints that involve functions of X. For example, there are typically angle difference constraints of the form theta L minus theta K. The difference across a line, the angle difference across a line is no bigger, the absolute angle difference is no bigger than pi on 4. Furthermore, there might be limits on angle differences not joined directly by a line that are effectively proxy constraints for stability limits. In addition, we could represent transmission line flow constraints as functional constraints in terms of the power flow equations. So if we put all those together, we would have functional constraints of the form h of x is less than or equal to h overline. A typical functional inequality constraint might limit the real power flow on a line that joins bus L to bus K. If we neglect shunt elements in the line models, the line flow real power flow function, PLK, that is a function from theta minus rho and u into r, it's defined by PLK is equal to the real power that flows out along that line less the losses. If there is a real power flow limit of PLK on the line joining bus L and K, then we'd represent that limit as the inequality constraint of the form PLK of theta minus rho u is less than or equal to P over line LK. And we could collect together all of these constraints into the inequality constraints Hx less than or equal to H over line. Remember back in section 3.7.1, we derived linearized versions of real power line flow constraints where we linearized voltage angles about a flat start. We could add additional constraints such as on complex power flow, proxy constraints due to stability and voltage issues, and basically any other sort of constraint that can be represented as a function of our decision vector into our inequality constraints. So that would yield a problem of the form 9.3. We want to minimize the dispatch costs subject to Gx equal to 0, subject to x between x underline and x overline, and subject to hx less than or equal to h overline. This problem is in general nonlinear and non-convex. Having said that, recent work has made progress on solving such general formulations directly. However, current electricity markets typically use approximations based on linearization, including DC OPF. And indeed, we will look at DC optimal power flow. The reason is that the general form of optimal power flow that we just presented has several difficulties. We have to solve a nonlinear, non-convex optimization problem, both in the context of day-ahead and real-time. That is more problematic for real-time, although in real-time we can utilize linearizations of actual operating conditions. In day-ahead we have more time, but in the day-ahead context we don't know exactly the operating conditions, particularly for reactive power and the implications for voltage magnitudes. So one simplification involves replacing the representation of the power flow equations with the DC power flow model and replacing the functional inequality constraints with a linearized version. This simplification neglects losses and reactive power issues and creates a linearly constrained problem. And the simplification is used in several day-ahead markets, requiring that the cost of losses and indeed compensation for losses and for reactive power be charged as uplift or separately incorporated into the formulation. Some markets such as New York, New England, Midwest, and PJM include losses as an additional consideration into the formulation after an additional approximation in the day ahead using the DC power flow approximation. So let's look at the formulation using the DC power flow approximation. We'll first assume that the objective depends only on the real power injections and that it is additively separable. Moreover, we'll initially assume specified values of real power demand, D overline, and of reactive power demand, E overline. We'll add demand bids for real power back into the formulation in particular contexts. We'll also assume that the only limits on the entries in X are generator constraints of the form P underline is less than or equal to P is less than P overline. Of course, more general generator constraints could be accommodated. We could consider reserves and other ancillary services as we have done previously. We could also consider limits on voltage magnitudes. And furthermore, we'll assume that the inequality constraints Hx less than or equal to H overline represents real power line flow limits only. So that gives us a simplified version where the system constraints are Gx equal to 0, Hx less than or equal to H overline. If we make real and reactive power explicit and separate out the net generation into generation and demand, we get the following. We've got our vector of P injections into the lines attached to the buses, collected together into a vector across all buses, minus the vector of corresponding generations equals minus the vector of demands. Similarly for reactive power. We have real power upper and lower limits, and then for all lines LK in the set capital K of lines that have real power line flow limits, we have our limit on the flow is less than P over line LK. If demand response was considered, then we'd replace D overline and E overline by D and E respectively, and then it would be natural to shift all of these entries over to the left-hand side of the equality constraints. We're going to further simplify the optimal power formulation by omitting the reactive power flow equations. This is really tantamount to assuming that we can satisfy them independently of other decisions. We'll also delete the reactive power and voltage magnitude variables from the decision vector, effectively assuming that we can satisfy all of the reactive power and voltage issues externally in a separate process that in fact fixes the voltage magnitude schedule, and we're going to fix it at a flat start. In other words, the vector of voltages is assumed to be all ones. We will linearize the real power flow equations and linearize the real power line flow limit equations. So we've now redefined our decision vector to be simply P theta minus rho. And now we've also redefined our last subvector xnp plus 1 as theta minus rho. Omitting the reactive power flow equations and fixing the voltage schedule leaves us with just the real power flow equations with simply mu U naught specified as the voltage magnitude. We've effectively neglected the reactive power and magnitude issues in favor of the real power issues. We're now going to linearize this power flow equation. We'll linearize the real power flow equations about theta naught equal to 0, the other part of a flat start. That gives us the DC power flow approximation. dP by d theta minus rho evaluated at the flat start times theta minus rho minus P is equal to minus D overline. We met this approximation back in chapter 3. Again, we'll assume that theta naught 0, u naught 0 satisfy the real power flow equations for zero net injections. And as in section 362, we'll define a Jacobian J that's equal to this matrix of partial derivatives dp by d theta minus rho, so that the power flow equations become J times theta minus rho minus P is equal to minus D overline. The real power flow limit equations then are for all Lk in K, PLK theta minus rho u is less than or equal to PLK overline. Again, linearizing these and maintaining u naught equal to 1, we again get our linearized about flat start approximation that says for all lines the rho vector d PLK by d theta minus rho times theta minus rho is less than or equal to P overline LK minus PLK evaluated at 0, 1. As in section 3.7.1, we define a matrix K to have rows given by KLK is equal to that row vector, and we define a vector D to have entries DLK is equal to rho PLK minus PLK 0, 1. Typically this is 0 again, since at a flat start the flows on the lines are 0, so that the line flow inequality constraints become K times theta minus rho is less than or equal to D. We can of course also add linearized versions of other constraints such as stability and voltage constraints into the formulation. The DC power flow problem therefore becomes minimize over P and theta minus rho the costs subject to the power flow equations, subject to the power flow line flow inequality constraints, subject to upper and lower bounds on generation. This problem is actually in the form of our generalized economic dispatch problem. Minimize x in Rn of fx subject to ax equal b, cx less than or equal to d, and in addition generator constraints. For the particular choice of x equal to p theta minus rho, corresponding to that choice, our A matrix in the form AX equals B, which is representing our equality constraint, would then be of the form minus I times J, because then A times X would give us minus P plus J theta minus rho, which gives me the first term in the equality constraints, the left-hand side. The right-hand side, therefore, should be B equals minus D overline. Similarly, Cx less than or equal to D can capture the line flow inequality constraints if we set C equal to 0 times K, so that C times X would give us K times theta minus rho, therefore necessitating simply noticing that D should be equal to the same D, and then the deltas and gammas is set up to produce a simple box constraints requiring the generation Pk at generator K to be between P underline K and P overline K. So now, having formulated the problem, we can consider the solution of the power flow problem, the optimal power flow problem, and then, since we've already figured it out for our general formulation, write down the pricing rule for offer-based optimal power flow, where each generator, K equal 1 through NP, offers an offer, which we'll assume equal to its marginal costs, gradient Fk, and also it specifies its limits, P underline K and P underline K, overline K. Let P star and theta star minus rho be the minimizer of this offer-based optimal power flow problem. Let lambda star and mu star be the Lagrange multipliers associated with the system constraints Ax equal B and Cx less than or equal to D respectively. As previously, let AK and CK be the columns of A and C, respectively, associated with the decision variables xk representing generator k, so that AK is minus IK, where IK is a vector with all zeros except for 1 in the kth place, and CK is 0 because there are no entries involving the decision vectors xk for the generators involving inequality constraints. And however, there are terms corresponding to the variables theta minus rho. They are indeed the matrices J and K correspond to the equality constraints and inequality constraints for the variable xnp plus 1. Our first order necessary conditions, just writing them down, look like this. And from previous analysis, we can simply write down the price, pi pk, the price paid to generators for generating pk, that would induce a profit maximizing generator to dispatch according to pk star. In particular, pi pk is equal to minus ak transpose lambda star minus ck transpose mu star. Remember, the entries of ck are 0 for generator k. The entries of AK are equal to minus IK, so that minus AK transpose yields IK transpose. In other words, a vector that's mostly zeros but a 1 in the kth place. When we multiply that into lambda star, it picks out the kth entry of lambda star. So the price to generator K is lambda k star, which is the Lagrange multiplier associated with the system constraint dpk by d theta minus rho minus pk is equal to minus dk. That is the power balance constraint for bus K. Price lambda k star is called the locational marginal price, or LMP, at bus K. And indeed, that means that the payment to generator K for generation Pk is pi Pk transpose. In principle, it's a vector, although in this case it's a scalar, times Pk is equal to none other than lambda k star times Pk. So generator K is paid based on the Lagrange multiplier on the power balance constraint associated with its bus. And similarly, demand at a bus would pay based on the Lagrange multiplier associated with its bus. If the formulation were expanded to include reserves and other ancillary services, then the LMPs would also include additional terms related to these services, as we derived for the case of reserves when we considered reserves without transmission constraints. However, having said that, current market formulations with ancillary services do not typically represent locational issues in detail. For example, there may be deliverability constraints for spinning reserves that are either not considered or only considered approximately in terms of deliverability to zones. Unfortunately, that results in some inconsistencies in such models. Let's utilize our sensitivity results. Typically, the LMP at a bus can be interpreted as the minimum cost per unit energy of delivering an additional infinitesimal amount of power to that bus, or delivering an additional infinitesimal or the value of per unit energy of producing an additional infinitesimal amount of power at that bus. And in this case, marginal means a derivative or infinitesimal change. So the LMP is the cost per unit energy of delivering an additional chunk of power to the bus. Typically, at least assuming that the conditions hold to apply our sensitivity theorem 4.14. And in that case, that sensitivity result tells us that the Lagrange multiplier on the constraint equals the sensitivity of the objective to a change in the right-hand side of the constraint. So the LMP for bus K is the Lagrange multiplier on the power balance constraint for bus K, and tells us the sensitivity of total costs, in other words, the cost per unit energy of delivering some additional power to that bus. The LMP represents the sensitivity of cost, of overall cost to changes in production. Recall that minimizing the cost minus the benefits is equivalent to maximizing the benefits minus the costs, or the surplus. And also remember from section 6.3 that this sensitivity of surplus is also called the marginal surplus. So the LMP is also reflecting the marginal surplus. Let me emphasize that the sensitivity interpretation is not always valid when the constraints are just binding, and therefore our sensitivity result is not directly applicable. So far we've considered offer-based optimal power flow, but considering the angles. I want to further reformulate the problem to eliminate the angles. This will help us to understand the relationship between constraints and the LMPs. It will also lead to a decomposition approach that can be used to represent AC power flow equations that we'll explore towards the end of the chapter. So recall the system constraints. Equality constraints, J theta minus rho minus P is equal to minus D overline. That's the equality constraints. And the line flow limit constraints, K theta minus rho is less than or equal to D. In section 3.7.4, we eliminated those angles by rewriting our equality constraint relating angles in P as a single power balance constraint, minus 1 transpose P equals minus 1 transpose D, or D overline, and theta minus rho is equal to J minus sigma inverse, P minus sigma minus D overline minus sigma, where sigma is the slack bus and rho is the angle reference bus. For reasons that will become clear as we discuss things, bus sigma will also be called the price reference bus to distinguish it from the angle reference bus. I'll conceptually distinguish these, but we will typically either choose sigma to be the slack bus to be the same as the reference bus, or sometimes in small examples we'll choose sigma to be a bus with demand, because that'll make some of the notational story a little simpler. With that reformulation, we can completely eliminate angles and obtain system equality and inequality constraints of the form, instead of equality constraints for each bus, just a single overall supply-demand constraint, and then inequality constraints on line flow, but now expressed entirely in terms of real power injections. If the demand was variable, that would be D, not D overline, and we would express it also in terms of the real power demands as well as the real power generations. The DC optimal power flow formulation with angles eliminated therefore becomes minimize over P, the costs subject to our single power balance constraint, our inequality constraints, and box constraints on P. This is in the form, again, of our generalized economic dispatch problem, but is a slightly different format. So to distinguish that, I'm going to write hats above my matrices and vectors to distinguish this formulation where I've eliminated angles from the angles where I kept the angles explicit. So in this case, X is just equal to P. There's no representation of angles. A hat, to make A hat X equals B hat match my equality constraint, I need A hat to be equal to minus 1 transpose. B hat needs to be equal to minus 1 transpose D overline. C hat needs to have the shift factor matrix embedded in it, namely K, J minus sigma inverse. But since I want to write it in terms of the whole vector X, which consists of the whole vector P, I'm going to define C hat to be the augmented shift factor matrix, which has got a column 0 that corresponds to the price reference bus, and I'm going to assume that the price reference bus is the first entry in P, and then I will write C hat X is less than or equal to D hat, and now D hat needs to include this whole vector here, so it includes k j minus sigma inverse d overline minus sigma plus d. So with this association, this generalized economic dispatch problem reproduces my DC optimal power flow problem. Again, I've got upper and lower bound constraints on my generators. In other words, my generator constraints are represented as follows. And again, let me emphasize that C hat is the augmented shift factor matrix that we derived back in section 3.7.5. So we're again going to consider the solution of the optimal power flow problem and write down the pricing rule for offer-based economic dispatch, where each generator k equal 1 through np. Again, it makes offers. We'll assume that the offers are equal to their marginal costs, and they also specify lower and upper limits. Let P star be the minimizer of the offer-based optimal power flow problem with the angles eliminated. And let me observe that if the offers are the same as in the previous case where we considered the angles explicitly, then the minimizer P star must be the same as previously in the formulation where we represented angles. Or at least to put it precisely, if there were multiple solutions, there has to be a solution of the angles included problem that has a vector P star that is also a minimizer of the angles eliminated version. Furthermore, the corresponding angles should be the same. In our angles eliminated version, let lambda hat star, mu hat star be the Lagrange multipliers on the system constraints. With that, furthermore, let's let A hat k, C hat k be the columns of A hat and CK associated with the decision variables xk representing generator k. So in particular, A hat k is equal to -1 and C hat k is equal to the corresponding column in the shift factor matrix if k is not the price reference bus. If it is the price reference bus, then it's the 0 vector. And this j minus sigma inverse k is the kth column of j minus sigma inverse. So if k is not the price reference bus, then ck is the column of the shift factor matrix corresponding to generator k, and each entry of ck hat represents the fraction of the generation injected by generator k that flows on the corresponding line. The entries of C hat sigma are all 0, since injecting and withdrawing the same amount of power at the price reference bus, or the slack bus, has no effect on any line flows. First order necessary conditions, we can just write them down. They're as we've seen before. And consequently, we can also write down the price P, price pi, pk, that induces each profit maximizing generator k to dispatch according to pk star. Pi pk, as previously, is equal to minus A hat k transpose lambda hat star minus C hat k transpose mu hat star. If k is not the price reference bus, then A hat k is equal to -1. So minus 1 just reproduces lambda hat star. Furthermore, we've just observed that C hat k is k, capital K, times j minus sigma inverse, the kth row of that matrix. So when we take the transpose of it, we get the transpose of those entries in opposite order multiplied into mu hat star. Again, let me emphasize that lambda hat star is the Lagrange multiplier associated with the system equality constraint. So in particular, the payment to generator k for generation pk is given by lambda hat star minus C hat k transpose mu hat star pk. That's the case if k is not the price reference bus. If it is the price reference bus, then it's simply given by mu hat star times pk. So generator k is paid based on lambda hat star, the overall supply-demand balance, less a term. What does that term consist of? That term is associated with the line flow limit constraints and is multiplied by appropriate shift factor terms. It is again the locational marginal price at bus K. In general, lambda hat star, the Lagrange multiplier on the overall power balance constraint, has a different value to the analogous Lagrange multiplier that would have been obtained if we ignored the transmission constraints. So it's not the unconstrained price that we might obtain from offer-based economic dispatch, ignoring transmission constraints. The LMP at bus K, lambda K star, is equal to the LMP at the price reference bus, which is precisely lambda star at the price reference bus sigma, minus a weighted sum of the Lagrange multipliers on the line flow limit constraints. Let me emphasize again that the weights are the shift factors to the constraints. So, the more significantly particular generators affect a flow on a constrained line, the more their price will be adjusted in forming the LMP. By the way, since the dispatch P star must be the same as in the offer-based optimal dispatch power flow where we considered angles explicitly, it must also be the case that the LMPs provide the same incentives. That gives us an important result. Consider the LMPs in the two formulations of offer-based economic dispatch. For some choices of Lagrange multipliers lambda star and mu star satisfying the first order necessary conditions of offer-based optimal power flow with angles included, and for some choices lambda hat star and mu star satisfying the first order necessary conditions for the angles eliminated version, we have that the LMP lambda star k is equal to lambda hat star minus c hat k transpose mu hat star. Moreover, the vector mu star is equal to mu hat star. If there are unique values of the Lagrange multipliers, then 9.4 and 9.5 hold for these values so that the unique LMPs are the same in both formulations. Okay. How do we prove it? Well, let's let P star be the minimizer of offer-based optimal power flow problem with the angles eliminated. Let the hat versions, lambda hat star, mu hat star, but mu underline star k, mu overline star k, be the Lagrange multipliers associated with the system constraints and the generator constraints. Let me define theta star minus rho to be inverse of J minus sigma times the appropriate net injections. Direct substitution shows that X star, lambda star, and mu star defined by 9.4 and 9.5 and the corresponding mu's satisfy the first order necessary conditions of optimal offer-based power flow with angles included. So we've proved that there is a correspondence. In the next section, we'll go on to provide some examples and generalize to some other results.